Our assignment aims to investigate Faraday's law and hopes to provide a basis to determine the magnetic dipole produced by a Magnetorquer. Faraday's law states that a voltage will be induced in a coil that's placed in a changing magnetic field. So here we have a Magnetorquer which is driven by an AC power supply. This provides a changing voltage in the Magnetorquer, which in turn produces a changing magnetic field. Inside the Magnetorquer we have what is essentially just an inductor. It's just a ferrite core which has got a copper wire wrapped around it. And we know that a changing magnetic field will induce a current in this inductor, which is then picked up by our differential amplifier over here. From this differential amplifier, a USB duct signal converts it to a digital signal, which is then plotted on the screen here. So we can see at the moment it's got a 1 Hz frequency. It's been driven by 1 Hz frequency, and the screen is also showing a 1 Hz frequency. When I increase the frequency of the driven magnetic field, we can see that the frequency and magnitude on the screen also increase. This is because the rate of change of magnetic field determines the magnitude of the induced current. We can also see that if the amplitude of the magnetic field decreases, the induced current reduces as well, and the same works for increasing the amplitude. Here we can see the same circuit again. This time we are not applying any filtering. We are driving this circuit with a 1 Hz magnetic field, and we are getting a 1 Hz voltage signal at the differential amplifier and on the screen here. You can see that there's quite a lot of noise here. It's very difficult to get any meaningful data. We can see approximate 50 Hz oscillation present. This makes it a lot harder to determine the peak-to-peak magnitude of the voltage, and from this, again, it makes it difficult to really find any sort of torque induced, as well as the actual voltage induced.